Okay. All right, so now we're going to continue on in module number 2, and we're going to be, or in module number 1, looking at part 2, which is going to be position and displacement analysis. So in part 1, we looked at chapter 1, and we were focusing on creating displacement diagrams for mechanisms, and we really got used to, you know, identifying the frame and then using the you know, the standard kinematic symbols to represent a more complex type of a mechanism. And we learned about 4-bar mechanisms, calculating mobility. So so now we're going to really kind of take it a step further. So you're going to notice when we click on module number 1 part 2, we're going to skip a couple chapters in our book. Okay. And I guess it's just a preference on how they decided to show this. Now, why is, hold on. I was gonna say, I know I have my book. I think when I moved rooms, I packed it away and I was a little afraid I didn't have it. So in the book, they start out with kinematic diagrams and they get everything all set up. And then they talk about CAD, and I think in chapter number 2, then in chapter number 3, they talk about vectors, vector additions and subtractions, which we will be using soon. And then they get back to the kinematic diagrams and they start moving them around and doing displacement. And I feel like, okay, we're on a roll with the kinematic diagrams and drawing them. Why don't we continue to reinforce that? But now we are going to have some dimensions and we are going to move things around. And that's really what the displacement is all about. So we're going to be looking at problems there. So I have the PowerPoint presentation here in PDF form, and this is going to be chapter 4, but we will go back to chapter 3 actually very soon. But for right now, we're gonna skip a little bit. So I'm gonna zoom out. And so if you want to open up your book to chapter number 4, that's where we're going to be. Okay. All right. So in this chapter, we're going to be looking at position and displacement of, you know, points in space. And really, usually it's going to be in terms of endpoints of mechanisms. We're going to be also determining the position of all the links in a mechanism as the driver moves. Okay, so we're going to be looking maybe at that crank rotating at some degrees or rotating all the way around. And now what's happening on the other end? How far did that slider move from where it was at? Then we're going to position all the links of the mechanism so that we can see them go around in an entire cycle. So all that means is we're turning the full 360 degrees, and then we're going to find out what's going on the other end. We're going to find limiting positions. This will get us the information about what is that furthest point on that very last link or the output, and what is the closest point. And then identifying that depending on the type of motion as either a stroke or the throw that is going to occur. And then finally, we're going to plot that information. Okay. So yeah, so we've got a lot to cover here. So as we look here in chapter 4, we kind of revisit that purpose of kinematic analysis, and really it's that those first steps in. I like to say we're laying things out right now. We're kind of just, you know, figuring out what is our spatial relationships, where do we have to fit it within, and what is the objective that we're trying to achieve with this mechanism. So kinematic analysis is going to determine what that full range of motion is, where the positioning of all of the links and such are, the extent or the range of the motion, and then also, you know, what is the space that we have to fit within. So let's talk first about position. So position of a point on a mechanism is where it's located in space in relationship to everything else, okay? Primary goal of position analysis is really just to determine the location of all of those links relative to one another in a particular like snapshot of time. So when we talk about position analysis, we're going to now have dimensions on our mechanisms. Okay. So up to this point, we were just kind of, or in our first chapter, we were looking at it in terms of, let's just draw it in proportion and make sure we understand the standard symbols and show it in the kind of that very stripped down generic sense. And just kind of getting a handle on that. Now we're going to be actually, you know, putting numbers to this, and now you're going to have to draw things to scale. Now displacement is going to be the end product of any motion that we have. So when we have things moving around, we need to determine, first of all, is this linear or angular displacement? And the difference between the two is if it's linear, it's going to be moving along a straight line. So the mechanisms that we saw early on in chapter 1 that had linear motion were going to be those crank sliders, right? So we have a crank on one end that's going around, it's connected to a connecting rod, and then we've got maybe a piston going back and forth, or a linear bearing, or a can crusher, or something like that, okay? So, so we're wondering, like, how far is that going to move as we rotate our input around? Okay. And then the other one is going to be angular displacement, and angular displacement is going to be looking at the other side. If it's not a slider, it's probably something that's either going to be another crank going around, or it could be rocking or oscillating back and forth, and finding out, okay, as we move our crank over here, what's going on over there? Okay. So angular displacement then is going to be that oscillation about a fixed point. So as we look at the beginning illustrations here, and specifically looking at 4-4 or sections 4.4 and 4.5, we're going to be erring on the side, as I've told you earlier, on graphical analysis. The book is always going to kind of give you both solutions. There's going to be, we call it analytical, or the math part of it, where we have to, put things in place and use our triangle, our math to kind of figure out where things are going. If you happen to have computer programming with me, we did actually an inline crank slider mechanism where we, did the equations and we figured out the displacement diagram. We'll be able to use that. If you didn't have me, that's okay. I have a copy of that Excel spreadsheet, and we'll kind of use it to kind of see what we can do there. But we're most often going to err on the graphical side, meaning we're going to be drawing these things out, taking the measurements, and then translating that data. Okay. I feel in the mechanical design program, you get a lot of experience running calculations, okay, and in a lot of other classes. So I like to take this opportunity to kind of get us back into, especially 2D CAD. You've been maybe away from AutoCAD for a little bit. Let's revisit it before you kind of like officially go out into industry, because it is going to be a skill that you want to kind of practice. So it's a great place to kind of bring AutoCAD back and use it to solve these problems. So when we determine the position of links, when we determine the position of links on all the links in a mechanism, I think that I misspoke there. When we would determine the position of all the links in a mechanism, I think it's supposed to say, as that driver moves around, we need to first draw the kinematic diagram in its like initial place. That may or may not be at the extent of the motion. So it may or may not be the furthest point out on that output link, or the closest point out. It might just be a snapshot in time, which is going to be most of the problems that you start off with here. Then you're going to always calculate those degrees of freedom, just to be sure that, number one, you have what you're expecting, that you then can confirm that you have your links identified and then your joints identified as well. Okay, so it's a nice double check for that. And then you're going to move that driver into a position from wherever you initially drew your diagram at. And then you're going to measure that displacement of the rest of what we call the slave links, the ones that are going to kind of go along when that driver moves. So let's look at figure 4.5. and then 4.9 and 4.10. I'm going to go underneath. Got to open up my camera. Okay. So on page 74 in your book here, you're going to find figure 4.5. So I'm going to zoom in here. And as we kind of look at that, that process that we just talked about, right now in the dark or the solid lines of our mechanism, we have the initial, if you would, placement drawn. So here you'll notice that number one is our frame, and it's actually connection in two different places to that frame. Number two, I'm going to assume is our crank, just because of number one, the lettering, but then also many times that crank is going to be a shorter link than maybe the other links that are in our mechanism. And then you're going to notice we're going to have this connector from B to C. This is going to be link number 3, and then link number 4 would be the output. Now, as we look here, a problem, as we were talking about now, first and foremost, position analysis is where are all the mechanisms at this point in time? And then additionally, we would be getting angles and lengths of each one of those links, okay? And then you're going to notice that they moved point, or that first link, number 2, and which is identified as from points A to B, but B, because that link is going to rotate about that point A, about that center, B is going to be the one that actually displaces. A stays in the same place because that link is rotating about that fixed position. So notice that we now have a new position for B, and they're calling that B prime, okay? And they moved that driver link 15 degrees, okay? So a question we would have then, and that's what they have illustrated here. Okay, so what happens now to link number 3 and link number 4 as the driver moves 15 degrees clockwise? Okay, so then what we would do is we would then follow up with adding in these other links to then show from their original position. We'll call this like home base, if you would. Where did they go from there? How much did they displace as that driver moved 15 degrees? Okay, probably not 15 degrees unless this is the same length, right? Okay, but it's not. So what we're going to do then is we are going to physically move them. So a graphical solution would be drawing this up in CAD, moving your driver, and now adding the other ones back in and seeing where they're positioned now. Okay. So that's how we're going to be using CAD in these cases. Now, to use CAD, we're going to look at that very same illustration. It's easy to move, our link, but then how do we get the other ones to follow along, if you would? So to go through this process, you'll notice that we have that similar diagram here. Let me get this straight. We move our driver 15 degrees. And now we want to figure out what's happening with the other ones, okay? Now, if we look, B is connected to C, right? B is connected to C. C can only go along this path because it's connected back to the frame on that member, or that link number 4, which rotates about point D. So in CAD, we can create a radius, or we can create a circle with a radius equal to, right, that length of that link. And then we can like plot that path, okay? And this is where, as you can imagine, notice that they're using different line types. You can then create layers with different line types and or colors in order to kind of keep things straight, okay? So this is the path that B goes along, and this is the path that C goes along, okay? They can only move on those curves just because of how they're constrained by rotating around either points A and or D, okay? Now, to find where point C is going to be, we know it can only travel along here. We would measure the length of that link number 3. And then from the new position of B, what would we do? We would strike an arc, right? Equal to that radius of the length of C. And then we'd have an intersection with the path that C is going to follow. And now that's the new position of C as B moved that 15 degrees, okay? That's what you're going to use CAD for. And using CAD gives you a nice accurate number for that. Okay. Gives you a nice accurate number for that. So if we turn our page here to page 76, we can see that very same scenario play out. So here you'll notice at the new position of B prime they identified, here's the radius of that B to C. And then they strike that arc, and now here's the new position where that intersection is along the path where C is going to go. Now we're going to intersect with that, and then we're going to redraw that entire mechanism. They don't end up redrawing it here in the book, but you can imagine how we would then draw to that intersection. That would be my C prime. I would connect those two, and now that I would then measure the angle from its original position to its new position. Okay, and we can kind of see it's going to be something less than 15 degrees in this case, okay? And then as a designer, what you can do is, okay, then you analyze, is that something that I want, for that? Is that going to satisfy what I need? And then you can maybe play around with lengths of the links to see how you can maybe get closer to a result that you might desire, Okay, those are what we call iterations, if you would. Okay. All right, let's go back to our PowerPoint. Yep, 4.9, 4.10, look there. So let's look at an example in the book here. This is example 4.1, and it's at the bottom of page 76. And what we want to do here, I'll go into our book. This is like, oh, okay. If I'm straight or not. It says here that we have figure 411, and it's right down here. All right. And it says that as that mechanism is driven by link number 2, we want to graphically reposition the links of that mechanism as link number 2 displaces from the position that it's in right now, 30 degrees counterclockwise. Okay. So we want to determine the resulting angular displacement of link 4 and the linear displacement of point E. So let's look. So you'll go ahead. Yep. So down here is the illustration, and they have it in its original position right now. Okay. So the job number 1 here will be to draw your kinematic diagram first. So this is going to mimic problems that you're going to have assigned. You're going to draw it in this position first, and you're going to add all of your labels, including your links and all of your joints. Okay. Then what you're going to do before you actually go ahead and start moving anything around, we want to calculate that mobility. Okay. And confirm that it has the number of degrees of freedom that we see to be how we can control this. So in this case, this is our driver, and notice that it says it has a degree of freedom of 1. So that means that we can just rotate this around, and that's going to be the only thing we need to do to get this slider to go back and forth, right? Okay. And as we look at it, it certainly looks like that's the case. Okay. So our mobility equation kind of confirms all of that for us. And if again, you forget to label a link, or if you forget to label a joint, it'll show up there, you know, with you knowing what the expected number of degrees of freedoms are. Okay. Then what we're going to do is we're going to go ahead and we're going to use CAD then to reposition our links into the position that they had identified. So in this problem, it said, okay, we're going to move link B counterclockwise 30 degrees. Okay. So notice that they started here at B, they rotated link number 2, and B is at the end point there. Okay. A remains in the same place because it is a fixed rotational point. It doesn't move. It's on the frame. So the only part that moves is going to be B, and it's going to move only around, you know, that circumference on that path. So here's our 30 degrees, moves back counterclockwise 30 degrees. Here's the new position for B. Okay. And now what we want to do is we also want to add in, okay, what is the path that any other of the other points are going to take? So as we look at link number 4, it also only rotates about a fixed center. So notice that point C here is going to only go along that path, or the radius of the length of link number 4. Okay, so that's just showing its path right now. And then as we look at the output, the other one that can move is going to be link number 6. And at the center of 6 is joint E. Okay. So now along joint E, we're going to, you know, show what is its path, and its path is linear. Okay. And in this case, it's an offset of 4 inches from point A, just to kind of give us spatial relationship, right? So this is going to show us what our paths are. So this is going to be something you're going to want to do in CAD so that you know these things can only move along those paths, along those arcs, or along those lines, depending on what you're at in the diagram. And then we're going to connect them. So we start with B, we put it to its new position, okay? And then we're going to strike an arc, as I say, and this arc is going to be the radius of the length from B to C. Okay, so this length right here, we're going to know that, we're going to measure it, and then we're just going to take that and we're going to strike another arc, and wherever it intersects, so you can see that line right there, or I'm sorry, that point right there where it would intersect, that's going to be the new position of C. Okay, so C is going to come back and actually be like this, right, in its new position, C prime. Then from that position, that connects back to point E. And this is the radius, the original radius from C to E. We're going to take that And now from this point where the new C is, we're going to strike that radius, that distance, and then we're going to find its intersection along its linear path in this way, in this case. So then now down below, you're going to notice we see the two positions. The first position is this one where the B is straight up and down, right? That was its original. And then any of the primes are the now new position when that driver moved 30 degrees counterclockwise. Now, the problem wanted us to know, I wanted us to answer, determine the resulting angular displacement of link number 4. Now, they didn't keep their link numbers on here, which I want you to for our purposes, but link number 4 was C to D here, okay? So you'll notice that they added the angle there for how it displays. So with this being 30 degrees, C to D or link number 4 went counterclockwise as well, same direction, but it only went 26 degrees. And then it also wanted to know, okay, what happened at point E over here? So E was pulled to the left, right? And then that resulting displacement. The displacement here has the symbol of what we call delta. That's kind of a universal symbol in engineering, math, science, of being like, how far did something move? What was the delta? You probably came across it if you've had physics yet. Okay, delta was used in those types of situations. So we reuse it here as well. So here's the delta, that's that triangle. And the delta for point E here is going to be 0.9544, probably inches, I would presume. Yeah, inches is, looks like what the original diagram was put in. Okay. So that would be a process that we would go through. So again, kind of reviewing, we're first going to draw the initial free body or kinematic diagram using like the snapshot in time. This is where we're going to be starting. Then per the problem statement, we're going to move that driver or whatever sort of result we're looking for. And we want to first determine what is the path of anything that is going to be what they call a slave link, something that's going to come along with the driver as it moves. And then we're going to finish up the drawing, mark off any radiuses, and then draw your final result, and then dimension to answer the questions that the problem is asking. Okay. Now, because we're using CAD, the beautiful thing about this is you're going to have nice, good results, and they're going to be to scale. So make sure when you are drawing in CAD, you are indeed drawing to scale. Okay. Additionally, and again, I'm not going to focus so much on doing demonstrations in AutoCAD because you've had that experience, and we kind of took our first time or two together to kind of show that process. But now you can probably see that when you're showing more than one iteration of a mechanism and we move these around, now in this case, you can kind of see one is lighter than the other, but it's not that easy to see. So I think line types become really nice. So you can maybe do a hidden line type for the next one, or a phantom line, or line weights might be nice, because that way, when you take your screen snips, colors would actually work well too with screen snips, because then you can see the different colors as well. So feel free to use that to help, see those differences in the different, if you would, phases of the mechanism and where it moves. Okay. So this chapter is all about, okay, we're gonna have the kinematic diagram, we're gonna draw it to scale, and now we're gonna move it around and see what happens. Okay. Graphical stuff, graphical solutions here. Okay. All right. Let's look at another example. I believe that's probably what's after. Yep. Example 4.2. So we want to go through this very same process, but this time we're going to be looking at a cutting snips. Okay. And we'll continue to look at the illustration here in the book. And I'm imagining that you are looking at this in terms of, oh, I can kind of see how they're going to be translating this into AutoCAD. And I like their illustrations too, so that you can get a good idea of what's going to be coming. So right here, we have a compound lever snips as shown. And they're often used in place of a regular tin snips when larger cutting forces are required. So using the top handle as the frame. So this is one of those tools like we had seen the last time, where okay, it's not really bolted to anything. So now we've got to pick something that would make sense to be our frame. And that might be like we did last time, kind of holding on to one of the handles and letting the rest of the tool kind of hang. And that's what they're doing here as well. So this top handle right here, the top portion is going to be considered the frame in this case. And it says, using the top handle as a frame, graphically reposition the components of the snip when the jaw is opened 15 degrees. Okay, so the jaw is over here. And that's really a practical problem because we want to, you know, maybe open that up to where we would normally want it. But then you probably want to see, okay, on the side where we're going to be putting our fingers in there, would it make sense or would it be reasonable for, you know, an average size hand to be able to open and close that for 15 degrees? So how far is that going to be? So first things first, we're going to draw that kinematic diagram exactly the way we see it here. Okay. Now they drew theirs just like this. Okay. Now you're going to notice that they didn't draw this as if you would like with very many points of interest. Okay. So your X is out here and it's going to be, if you would, right here. It's going to be its initial position. So right there is point X on the top jaw. Okay. And then as we look here, they really didn't measure the bottom portion. They're kind of using this as the frame of reference as kind of like 0 degrees, if you would. And then they're moving it. This is the 15 degrees there, which would translate the other side to be 15 as well. Okay. Right. So now it's open 15 degrees. And now we want to find out what happens to the other side, right? So when we look over here, we want to find out, all right, where is this going, right? So if this is my handle, this is going to remain part of the frame because that's the top portion. This is going to stay where it's at. How far do I have to open up in order to, you know, get it that 15 degrees, right, with my hand? And so that's going to be this triangle over here. Okay. Now, as I said, remember, if you look at this, and the book tends to stick with triangles is like their standard, but we've seen where we can use other types of shapes to represent more of, you know, a design problem if you want to incorporate a little bit differently looking, if you would, output so that it more represents the type of special interest point that you have in mind for the design. So if you're like, oh, I wouldn't have done a triangle, that doesn't mean that it has to be like that, just so that you know, we were, you know, you can get a little creative with this as well. So anyway, so this is going to represent that initial position of our handle. And then once we move this 15 degrees, notice that we strike the arcs to show the paths and the differences. And then down here is going to represent from its initial position, which was Y, to get to Y prime, this is now going to have to open up a total of 34.4 degrees in order to get 15 out of this side, okay, to open that up. So then now let's say I'm, you know, I'm developing a new hand tool. What would the next step be then? You know, if I look here, it's one thing to have it on the computer screen. What would I do next to possibly kind of see if this seems like it's doable? Ideas. What was that? Sure. Yeah. Like take the measurements, get physical, right? Like kind of see like, okay, if I have my hand here and I go like this, what is it? You know, is that 34 degrees reasonable or not? What else could we do? No. I'm not worried about forces, my friend. Remember, we're in kinematics. We're only worried about displacement and position right now. So not worried yet about forces. That'll come. But in this initial time, we're just kind of trying to figure out, you know, that. So how would I be able to test? Could take some measurements. What's another thing that I could do to test this, like the next step before I would, if you would, release it to production, or maybe even start looking at forces? Maybe create a model of some sort. Maybe it's 3D printing. Maybe it's having some parts made up. Maybe it's, you know, mocking up an existing one so that I can see if this is actually going to work. Yes. So kinematics is this level of let's kind of feel it and see if this can work. And we'll get that opportunity in this class to do that in a couple cases. So, so yeah, you know, this is where you're figuring out ranges of motions. And, you know, a practical example like this, when it's a hand tool, it makes a lot of sense. And then you can have maybe a couple different people try it out too and see, is that comfortable? How does it feel? When we look at mice, right? Mice used to be, well, and they still are, got one over here on the desk, just kind of like, you can't really see it, but like this, right? Just the regular kind of flat, regular kind of mouse, right? One of these. But they can get pretty fancy. I mean, mine's not even the fanciest, but if you're a gamer, there's like, you know, very fancy ergonomic ones. Keyboards, same thing. And how do you determine that? You know, how do you determine what's really, you know, comfortable for somebody? Is you have people hold it in their hands. You have them critique it. You have, you know, you kind of mess around with it. And 3D printing then makes that process a lot more rapid, if you would, right? So that we can get those iterations a little bit sooner. Okay, so kinematics is in this layout, this initial design, figuring out, you know, type of place in the design process. Okay. And yeah, I know it. You want to jump to forces right away. We want to jump to what are the materials, but not in kinematics. We're only worried about how, you know, how this is going to move. And in this case, how is it going to feel? Does it make sense? Okay. All right. Okay. Let's see where we're at on our PowerPoints here. Okay, limiting positions. And again, focusing on graphical analysis side of things here. So limiting positions is when we have a configuration of a mechanism and we place it in its furthest and closest away, or in what we call limiting positions. So when I go around in my entire cycle, where is the extent of our output going to be? Now, that could be a stroke. A stroke is a linear distance, meaning it's going along a linear path. And we want to know, like, how far is it at its furthest point out and how close is it at its closest point, but then measuring the distance between the two. Okay. So for instance, if I'm, you know, 2 inches out from my driver and I come back in 1 inch, the difference between those two would be the stroke, like how far I lost my words, how far that slider went back and forth. Okay. But if I'm talking about something that oscillates, then I use the term throw. Okay. Throw means how many degrees did I actually go through, you know, total from my furthest to my closest point, if it's something that's going to rock or oscillate. Okay. So if we look at figure 425, now we're going to be skipping over some things here, some sections, and those are sections that are going to relate to the analytical part of things. So, so if you really like math, you can do that for yourself for extra credit, but we're going to skip over and we're going to go to page 88. And when I go underneath page 88 here, we're going to see an example of each of these. So at the top, we have a slider crank mechanism. And you're going to notice here that as the crank rotates all the way around, we're going to see how point C gets either closest or further away on that line of action. Okay. And it's going to be linear because it's a slider. That's considered the stroke. The furthest, the difference between the furthest and the closest. How far did we go? What's that total distance that it travels? When we're here and we have something that oscillates, as I said earlier, we have the crank going around and doing its thing for 360 degrees. But what angle is it at when it's at its closest, you know, on that output? And then what is that angle at that's furthest? And the difference between those two is the total throw. Okay. All right. So problems that we're going to be solving here in the kinematics homework is going to be, now tell me, what is the stroke and what is the throw? What is that total? Okay. So we have problem 4.6 here. Problem 4.6, we've got a mechanism and it's a reciprocating saber saw. Okay. And we want to determine the limiting positions of the actual blade itself. Okay. So first things first, draw our kinematic diagram in the position that we see it right here. Now, this is no particular position. It's just in a place in its entire cycle. And so we're just going to duplicate what we see there. And what we have then, if we go over here, here is our kinematic diagram. Okay. So we've got link number 1, which is our frame. Link number 2, which is going to be the radius to the connecting rod that goes down to where it's constrained back or up and down. Okay. And then that's going to be our link number 4, and that's going to be our slider. And then we have A, B, C, and then they didn't label it, but D is going to be the joint of that slider, like on whatever is keeping it in place. Then you'll notice that over here, what they do is they are going to show where each one of these links, like what is its line of action. So in this case, our line of action for our output for the saber saw blade is it's going to be linear going up and down, okay? And then we have our radius of our driver going around, and then the length of that connecting rod is going to be important to us. Now, for limiting positions, there are two positions that this can be, and that's going to, give us its furthest and its closest. So first of all, if we take, I'll point to this one. If we take this radius and our connecting rod down to our slider, and we put them in line with each other so that they're straight. And that's what we see. I'm going to show you in this configuration here. We see B in line all the way with C. So this is like in its furthest position down. And we strike that arc of link number 2, its length, plus link number 3, its length. And that's what we see up here in the construction. So from A, when link number 2 and link number 3 are straight across, this is going to be their length. And then where they cross over, the travel of that slider is where their position will be in its furthest down position. Okay, its furthest down position. And then where it's going to be in its uppermost position is where this comes around. This is going to be B coming around, and where B overlaps the total of B to C. Do you see that? They're like one in front of the other now. So B is overlapping and C is coming across. That difference is going to be where we cross here. So this is going to be link number 3 minus the length of link number 2. And where that crosses here, that's going to be its furthest up position for that slider. Okay. Now, as you're looking at this, do you kind of see how you would use CAD for this situation? Everything is going to be circles and their radiuses are going to be these lengths. Okay. And by doing the limiting positions, the furthest place down, the furthest place up, then the difference between those two, this number is going to be equal to the stroke. Okay. Because it's a linear distance. Any questions about that process? Now here too, again, as we look at kind of where it was at, we'll notice that we have 2 other positions here. We have its initial position, which was like kind of in the middle of the cycle. And then we have its furthest down, and they were calling that C prime, for instance, and then the B prime. And then its furthest up is C prime prime and B prime prime. Okay. When you do it in CAD, colors would probably be great, for those different positions, as well as you could even use, like I said, line weights or line types. Okay, feel free to exercise those. Questions? Yeah.
So the 1-inch dimension on figure 426, that's basically just a reference for our initial dimension.
Yes. So over here, 426, notice that we have some dimensions in place, and I think that's only to get kind of the angle that you're at. So right now, this is an offset from the rotation. So if this is our rotation, this is an offset dimension to the number 1. So this would be the middle of our slider going up and down. Yeah, so it's just that offset dimension. So over here, it would translate to this distance right here, 1. Distance 1. Oh, here's another one. So let's turn our page. Okay. So we looked at number 6 and then example number 7. Now, example number 7 is really the very same process. Okay, the very same process, except this time we're not looking at a slider on our output. We're looking at an oscillating or a rocker. Here we have a water nozzle and an automatic car wash, and we want to determine the limiting positions of the mechanism that places the nozzle down here in its extreme position. So it's furthest up and it's furthest down. Okay, so in a car wash, that's kind of important, right? Because we want to be able to kind of sweep the sides of the vehicles that we say can go through there and get clean, right? So we want to know how high that's going to go and then how low. Now, is this called, what is this called when we want to know that difference between the high and the low? It's not stroke, it's, do you remember the term? It starts with a T. It's the throw, exactly. So we want to know what is the throw of that nozzle so that we can see if that angle is going to be appropriate for the vehicles that are going to go through there, okay? So we're going to draw first our kinematic diagram. This is a motor. We have a crank associated with it. So this is going to be our frame right here. That's not going to move, right? This is going to be our link number 1, link number 2, and then link number 1 is our frame. Link number 2 is going to be our crank. 3 is going to be that connector, okay? And then this is going to be the link that's going to oscillate back and forth, and it is connected over here back to the frame again, okay? So we're going to draw first our kinematic diagram of this water nozzle mechanism in the position that it's at. And that's what we see right down here on the left-hand side. So they took those dimensions. Now they don't have it dimensioned here, but they have it drawn to scale, where this is the center of that motor. Here's our link number 2, the crank. Then we've got our connector back to the nozzle. Now, technically the nozzle is out here a little bit, but they didn't worry about that being a any sort of a point of interest. But if you wanted to add it, you certainly could. Okay, that wouldn't hurt. And then now what we're going to do is we need to determine, okay, what is going to be the travel of each one of these points? So as we look at link number 2 here, it can only go around in a circle, right? And so its path is simply going to be that circle. Link number 3, as it's connected here, it's going to have its radius right here. And then link number 4 is going to be another radius. So you see those arcs struck on our very next illustration here to show the travels, okay? Now, additionally, when we start looking at limiting positions, we're going to take those 2 links, links 2 and 3, they control 4. And when 2 and 3 are in line with each other or adding together, they're going to be at their furthest point out. So you'll notice that they created an arc that adds together those 2 lengths. And that's going to be the furthest point out down here where this intersects with the path of C. That'll be C's furthest point down. And then its furthest point up, if you would, in relationship. Now we're going to take that length number C and we're going to, if you would, overlap it as it rotates around with B. And then that's going to be L3, the length of L3 minus L2, or the length of each one of those links. And then that radius is going to also strike on the path of C. So now the furthest up it's going to go is this one, and the furthest down it's going to go is going to be that one. Okay. And now we want to show those 3 positions. Okay. So again, I think there's better ways of showing these. Again, colors will be helpful. Line types would be helpful as well. But the result here is that from the C prime prime in the uppermost position to the lowermost position, that difference as we go around 1 full revolution on our crank, we're going to have 47 degrees. Okay. And then we can determine, okay, we can lay it out with inside of the car wash and see what the different sizes represent, the different sizes of the cars, and see if that's going to be okay. All right. Questions? All right. So kind of looking at limiting positions with two different types of mechanisms that are very typical, again, with a stroke, linear distance, or a throw, which is going to be that difference between the oscillation of a mechanism. All right. Displacement diagrams. Okay, displacement diagrams. Displacement diagrams are going to give us a nice pictorial of what's happening with this cycle, okay, as we go around. So I'm gonna kind of skip ahead to page 99. Page 99. So if you want to go underneath, or if you want to look at your book and go to page 99, you're going to notice at the very top here, there is example, the problem statement is on the previous page, on page 98. And this is a driving mechanism for a reciprocating cylinder. And we want to plot a displacement diagram of the piston displacement relative to the crank shaft rotation. Okay, so here is the crank, and this is going to go around on that center right there. And what's going to happen is this is connected to the connecting rod and then up to the cylinder. And that cylinder is constrained vertically to go straight up and down. So as this goes around, this cylinder is going to go up and down within the inside. I'm sorry, the piston is going to go up and down within inside of that cylinder. Okay. Now to represent that kinematic wise, we see it's a simple slider crank mechanism. Okay. Our slider is right here. This is going to represent our piston, connecting rod, and then our crank is right down here. Now, if we draw that to scale using the dimensions that they have here, then we have the very, it's going to be a representation of exactly that. Now, this is considered what we call an inline slider crank mechanism. Okay. All that means is that our crank is in line with the slider. There is no offset distance. Okay. On the example that we looked at just a little bit ago. Okay. On this example, okay, this is an offset slider crank because we don't have the center of the crank in line with the actual slider. So over here, there is an offset distance. Okay. They're not in line with one another. So this is an offset. And the one that we're looking at is going to be an inline. Okay. An inline. Now, as we look here and we, we start to want to analyze what this motion looks like on a displacement diagram, I'm going to kind of jump ahead to that on the next page, on page 100 at the bottom. This is a displacement diagram. And this displacement diagram is going to show the crank angle, okay, the crank angle to piston displacement, okay, piston displacement. So when we look at crank angle, we're going to go back over here. Right now in the position, crank is our link number 2. And in the position that it's at, notice that we have completely in line link number 2 and link number 3. This is one of our limiting positions, meaning it's in its uppermost position right now, or on a piston arrangement. Anybody know what we call that? Top dead center. You've maybe heard of that before. Top dead center. So that's the highest that piston is going to go. And then when it rotates around and it gets down here and we get the overlapping effect, that's going to be its furthest point down, and that's called bottom dead center. Yeah, top dead center, bottom dead center. Okay. Like again, if you've been around engines a little bit, you may have heard of that terminology before, but that's exactly what that is. Okay. So when we go around one cycle, we go around, down, and all the way around. We want to know what's going on here. Okay. So this displacement diagram is a graphical representation of 360 degrees of crank rotation and how far that piston goes up and comes back down as it goes along its travel. Okay. As it goes along its travel. So I want to show you, I have a little bit of extra information in our module. So if we go to part 2 and we look at the inline slider crank model PDF here, this is one of the references that I have for a handout for you. Now, if you had computer programming with me, this is going to look familiar. Okay. So this is what's going on, if you would, every 45 degrees around that crank. Okay. So over here on the left-hand side, this is going to be the representation of when we have that crank in line. So we've got 1 inch on my crank, 3 inches here, and the total distance from the center of rotation of that crank all the way up to the piston is 4 inches. Okay. We call this, like we said earlier, top dead center. And we also call that crank angle 0, because it's one of the limiting positions. Even though we might say, well, that crank, if we look at the crank down here, technically it's at maybe 90 degrees from like normal 0, but no. When we determine our limiting position, we now pick one of those to be crank angle 0, because that's like the start of a full cycle. Okay. Because we're out on one end of, in this case, a stroke of the piston. So we've got this extended, that's going to be crank angle 0. And now we're going to move it from that initial, what would be up 90 degrees, crank angle 0, we're going to move it counterclockwise 45 degrees. Now, what's going to happen is that piston is going to only be able to go along that vertical line. But as this rotates 45 degrees, it's going to like pull it down. Do you see that? It's going to pull it down. So now, because of 45 degrees of rotation, we got a delta, a displacement of 0.377 from its initial highest point. It came down, right? So that displacement, this number right here, if we go back underneath and we find on our graph where 45 degrees is, now it's not these numbers, but if we find where 45 degrees is, that should be the number that we correlate to our piston displacement. Does that make sense? Okay. So like this is 0 right here. This is like top dead center. And then any movement that we get is then going to be off of that. So if we go back to that illustration, we're going to move it then another 45 degrees. So now we've got our crank at 90 degrees. And now it's pulled down a total of 1.172. Okay. Now we're going to continue to go around another 45 degrees. Now we're at 135. And now it's down a little bit further. But again, notice our measurements are always coming from 0 down to its new position. That's the number, this delta. So 0, 0.377, 1.172, 1.792. Those are the numbers that we're plotting our displacement diagram. So if we go back over here, okay, those are the numbers that we're going up, up, up. Okay. Now we're at 135. That was the one that we just looked at. Okay. We're still not to the very top. So if we go over back again, you'll notice that when we get to that 180 degrees, now we're over the top of each other, right? That's the lowest this can go. That's the lowest that this can pull down. Okay. So this is going to be our bottom dead center, and our total delta here is 2 inches. Okay, 2 inches. It went from that initial all the way up to the top down. And now that difference between the two, the stroke, is 2 inches. Okay. Now on an inline crank, because this is inline, when I start going back in the opposite direction every 45 degrees, it's going to be the mirror image of what we just saw earlier. Okay. So that means that when I come around on this side and I go 45 degrees continued, I'm going to be back to 1.792. And then I'm going to be back to 1.172 and so on. And then back to 0 when I get there. Okay. So in line is a mirror image on either side. If I am an offset, unfortunately, it's not a mirror image. Okay. It's not a mirror image. And you get to do one in line and you're going to do one offset. Okay. It's going to be very similar, but yeah, you're going to do a displacement diagram for each. Okay. Now to aid us in this, in the inline, for those who had computer programming with me, okay, we had a spreadsheet. Do you remember seeing this? Okay. And we kind of explained it, and hopefully now as being in kinematics, you have a better picture of what you were really looking at. Okay. In there, we were kind of introducing this idea and said, okay, we're going to be able to use this spreadsheet a little bit later. So here it is. So I'm going to go back to our module, and you'll notice that in that part 2 module, just below, we have it says assignment 4. Don't worry about the assignment 4. That was in computer programming. That was the assignment that it was. So if you wanted to, for those who had it with me, if you want to go back to your module 4 work, but I have it here as well. You can download this Excel spreadsheet. Okay. And by doing that, if I go and I pull up my spreadsheet, this is the spreadsheet that we created. Okay. All right. So what we did is we used the equations from the analytical portion of the book. And again, I'm in kinematics. We aren't worrying about that. We set this up in computer programming, and now we're going to use something that we created. If you took this previously, I think you may have created a similar one. If you took it with, I think, Randy, did he teach computer programming? I think, right? Oh, you have an offset one? Oh, then you can use it for your offset one. Okay. Now, it's not going to be, I'm not going to leave it at, for instance, then you might want to share with the people around you. I'll explain the assignment in a little bit, but let's look at how this works. Okay. So your crank angle, the number of degrees that you have. Now, remember, crank angle always starts from 0 degrees, and 0 degrees is going to be identified by your top dead center or your bottom dead center, whichever one you choose to be your 0, like your starting point for your crank angle. And then because it's Excel, it was easy enough to have it every 5 degrees, plot out my numbers. Okay. So you'll notice here that the first column is our crank angle, starting with 0, going every 5 degrees. And then we have our displacement, our delta. Our delta at 0 degrees, that's going to be our top dead center. And then as it goes down, it's going to be 5 degrees, 5 degrees, 5 degrees. And then it's going to be looking at that delta of that piston moving down and always measuring from that initial 0 degrees at the very top. Okay. And then the rest of this, the Y, the alpha angle and such were part of the mechanism. Now, what you want to be aware of is L2 and L3. L2 will always be your crank. Okay. Because that's going to be, you know, the designation for it. L3 is going to be your connecting rod, right, to your slider. So in our case, for this illustration, we have a crank that is 0.75, okay, and then we have a piston that is 2 inches, okay, 0.75 and 2 inches. And then you'll notice that our stroke is automatically calculated here at 1.5 inches. Okay. So if we go forward and we look in our book, whoopsie, wrong one. Back over here and we go underneath here. If we look in our book to page 100, the highest point on our curve is 1.5 inches. Okay. Now let's see what we have here. If we look at the Excel spreadsheet, you input over here the yellows, and then your output here is going to be your stroke, and then the other output is going to be the displacement diagram. So the crank angle is on the bottom here, okay? And then the piston displacement is going to be your vertical axis, and then you're going to notice that it plots each one of those points over here on that displacement diagram. Now, because it's an inline, it's a mirror image after we get past 180 degrees. So if we go over here on our spreadsheet, okay, we're going to notice that at 180 degrees, which is right here, if we look on either side, okay, of our, I should look like this one, at the displacement on either side, you're going to see that they're the very same numbers. Okay. And that's the nature of an inline. It's going to, you know, just kind of do its mirror image on the opposite side. Offsets do not do that. Okay. Offsets do not do that. Right. So, so any questions about a displacement diagram, it truly just gives us that graphical representation of what the displacement is in relationship to crank angle. Okay. And I like to imagine like this down here, this line right here is my 0 degree reference, which on my, let's see, if I went back too far, hold on, go back. If I look back on that diagram where we had the sketches, this is 0 degrees right up here. And so you're plotting this distance each and every time. Okay. And it's always a reference back from 0 degrees. It's not the difference between the last movement. It's back from your initial 0 degree angle. Okay, that's going to be the value that you plot on that displacement diagram. Now, I'm going to have you do a little bit of work to prove some numbers, but then you can use the spreadsheet. So if you have an offset one, great. Okay. I'm giving you the online one if you didn't have me, or if you had me in computer programs, in computer programming, you can use that. And then we're also going to be doing an offset, and that one I have assigned as manual, that you don't have to use an Excel spreadsheet if you don't want to. So let's look at, because I think this should bring us to the end of our PowerPoint. Go back to my PowerPoint. I know we were towards the end here. Okay, displacement diagram. We looked at that example, moving every 30 degrees. Okay, all right. So any questions content-wise at the moment? All right, then let's take a peek at our homework. Okay, I'm going to stop this for a little bit, and I'll do a separate little video on the homework overview. So I'll be back.